Hi everyone, hope you're doing well. For this section, we're going to be taking a look at a variety of techniques that we can use to help us to evaluate limits. The section 2.3 is calculating limits using limit laws. So there's a set of laws for limits that show us how we can apply the limit in a symbolic sense. So we'll be doing a lot of algebraic evaluations of limits here. But we'll still be using graphical and numerical approaches when needed as well. The direct substitution property, which is property defined for the continuous functions, polynomials, and rationals, which are continuous on their domains. More precise definition of continuity is coming up in a couple of sections. But this means that when we are dealing with a polynomial or a rational function, if we are taking the limit as x approaches a, where a is within the domain of the polynomial or rational, then we can just substitute the value a into the polynomial or rational to evaluate it. We'll take a look at some limits of the indeterminate forms. The indeterminate form that we are most familiar with right now comes from when we are doing something like a difference quotient, when we get that 0 over 0. Okay, we previously saw how we can apply algebraic technique to a 0 over 0 situation if we had a rational function. That's a polynomial of a polynomial. Recalling that if a polynomial is equal to 0, then that means that there is a factor of that polynomial that we can easily find. Okay, if the 0 of the polynomial is, let's say, c, then the factor of the polynomial would be x minus c. Then we can remove that discontinuity, remove the factor by canceling from the top to the bottom. Now that works well when we're dealing with a polynomial or a rational function, a ratio of polynomials here. We want to be able to take a look at limits when we're dealing with other kinds of ratios, quotients, which result in these indeterminate forms, such as 0 over 0. We'll take a look at piecewise and absolute value as well. The absolute value function can be expressed as a piecewise function. We call absolute value of x. The absolute value can be interpreted geometrically as distance from 0, so we always get a non-negative value when we take the absolute value of a quantity. But we can split up the absolute value of x piecewise. We can define the absolute value of x is always just equal to x itself, as long as x is greater or equal to 0. Right? If you have a positive number, the absolute value of that positive number will just be itself. But if the value of x was negative, right, if the original value of x was already negative, then the job of the absolute value would be to flip the sign of that to make it negative x. So we would have a piecewise model for our absolute value function. This is consistent also with the graph of an absolute value function, which would look like this. So it's like the line y equals negative x when we're on the domain from negative infinity to 0. And it's like the line y equals x when we are on the domain from 0 to infinity inclusive, so including the 0, that is. Okay, but we'll take a look at more complicated examples when we're taking limits involving absolute value and how we can design piecewise models in order to evaluate those limits. And then the squeeze theorem, to introduce that, we'll take a look at the textbook provides a couple of nice animations that I'd like to show you here to bring your attention to demonstrate why the squeeze theorem works and how we can apply it in some examples where it may be applicable. Now, I've included along with this lecture video a couple of things, a couple of handouts. One, there's your worksheet. There's some exercises on it. So I may do a couple of these in this lecture video. Okay, I think I'll do this one right here, 2b, with the absolute value in it. You can see where we're going to have to deal with the absolute value, and I'll do that piecewise. And I'll do maybe this one right here, which is an example where we can apply the squeeze theorem. Okay, so there's your worksheet. And also some notes I printed out for you to try to condense all these limit laws, the main properties and laws, to try to keep straight for this section. You can see that there's several limit laws. Okay, all of these laws as written are going to require that, well, first that c is a constant, and then we have the functions f of x and g of x. But we're going to require that the limit as x goes to a of f of x and the limit as x goes to a of g of x each exist in order for these laws to actually work the way that they are written here. Now, I'd also like to show you an example of where you can evaluate a combination, a limit of a combination of functions, if one or both of them doesn't happen to exist. Okay, but this is saying that in order for the laws to be used the way they're written here, to guarantee that they would work, we would need for each of the limits individually to exist. For example, this product law right here, the limit as x goes to a of the product f of x times g of x, can be evaluated as the limit as x goes to a of f of x times the limit as x goes to a of g of x, but only if each of these actually exists. If we think about that, conceptually, it seems to make sense. If one of these two limits wasn't to exist, well, then how would we be able to find the product of those two things? When you multiply something that doesn't exist by something that does, ultimately the product itself wouldn't exist. Okay, but if we are dealing with the limit of a product of functions, it doesn't mean that we can't try to see if we can rewrite the product itself to rerun the limit on the result of that product. Okay? So if I had something like the product 1 over x times x, and I wanted to run the limit, let's say, as x goes to 0. Note that the limit as x goes to 0 of 1 over x by itself. Think of the graph of y equals 1 over x. What happens when x approaches 0 on the graph of y equals 1 over x? You're approaching a vertical asymptote. On one side you're going to infinity and the other negative infinity. So the limit as x goes to 0 of 1 over x, that would not exist by itself. But if we had the product 1 over x times x, or let's say 1 over x times x squared, or something like that, then what we could do is we could first take the product of the two. 1 over x times x is just equal to 1. Then we could run the limit on the product. Right? So the idea, again, here is that you can use these laws the way they're written. In other words, like this law right here, you can split it up into two separate limits and multiply them together. But you can only really do that if each of those limits ended up existing independently. All right, so there's a lot of room here maybe for some interpretation and there's maybe some ambiguity here. Let's just put this into practice and try out some different examples. And the more examples we work on, try to build sort of an intuition about how we can use different techniques to apply to different types of limits that we may be looking at. Okay, so there's a total of 11 limit laws for us to look at here. Let's see, some interesting ones. The root law. Okay, so square roots, cube roots. Okay, for instance, you can move the limit inside of the radical, okay, inside of the radical, right, under the conditions that first n is a positive integer, okay, and also if n is even, then we have to assume, or we would assume in general, that the limit as x goes to a of f of x is greater than 0. That way we're dealing with real valued functions here. Recall that if n is even, let's say it's a square root or a fourth root or something like that, but the resulting limit as x goes to a of f of x, if that were a negative quantity, then when you apply the even root, you would get imaginary numbers potentially. Right? Well, we want these to just be real valued functions at this time. If you're not told ahead of time whether it's real or complex, the assumption is that you're dealing with real valued functions. Okay. The quotient law, similar to the product law, you can take the limit of a quotient by taking the limit of the numerator and the limit of the denominator. Okay? And that would be fine as if the limit of the denominator is not 0 itself. Right? But wait, didn't we already do that recently? We had denominators that were going to 0. Like difference quotient, right? Recall that when we did the limit of a difference quotient, the limit of the numerator was 0 and the limit of the denominator was 0 as well. But how did we perform the limit? How did we actually take the limit? Okay, we didn't take the limit by letting the denominator become 0. Right? We used the fact that it was 0 to say, well, then there's something else we need to do to the quotient. And what we did is we then manipulated the quotient algebraically to rewrite it, like removing a discontinuity, for example, so that later we could rerun the limit on the simplified quotient. Okay. Now, if it turns out that the denominator does not go to 0, by the way, for a quotient, then just take the limit of the numerator and the limit of the denominator and see what you get. In other words, you're not going to need to remove any discontinuities if there isn't a discontinuity to begin with. If you don't get 0 over 0, then there's nothing to remove. You can just run the limit of the ratio, as long as there's no other issues to be concerned with. And we took a look at examples with infinite limits as well, where you had a finite number from the top, but 0 on the denominator. And there you might want to use a graph to look at the asymptotic behavior around the vertical asymptote, or a numerical approach, where you can plug in values from the left and from the right in order to see what the value of the quotient is approaching. So we've already taken a look at this a bit. Okay. Continuing with the quotient law, right? If f of x is equal to g of x when x is not equal to a, then the limit as x goes to a of f of x equals the limit as x goes to a of g of x. So as to say, if you were to simplify a quotient, let's say, or a function in general, right? If you were to simplify the function to make it look like another function, in other words, if you were to cancel out a factor, that's one way that we could do that. I show an example down here. Right? If f of x is 3x plus 6 over x squared plus x minus 2, for instance. Well, in this case, right, if x were equal to negative 2, right, you would get 0 over 0. Well, so that means that f of negative 2 itself does not exist, because 0 over 0 is not a number. Right? But it is an indeterminate form. Meaning that if we were to take the limit as x approaches negative 2, remember that means that we are not choosing negative 2 to plug in. We're choosing and thinking of values that are very close to negative 2 to the left and the right. Okay? So because we're choosing values that are not necessarily equal to negative 2, okay, we can remove the discontinuity from here. Now we can examine another function, 3 over x minus 1, which is the same as 3x plus 6 over x squared plus x minus 2. It's the same as that function everywhere except where x is negative 2. So we did that in the previous section where we would take a function. We did a couple examples like this. We take a function, okay, that was undefined, okay, and it turned out it was indeterminate. And when we created the graph of that function, we ended up with a graph of a simpler graph that had a hole in it. Right? So if we were to, for instance, graph this function, y equals 3 over x minus 1, the only really interesting characteristics on the graph of y equals 3 over x minus 1 would be that there's a vertical asymptote at x equals 1 and a horizontal asymptote at y equals 0. But if we were to take a look at the graph of f of x, 3x plus 6 over x squared plus x minus 2, that graph would have the same asymptotes as we just talked about. It would also have a vertical asymptote at x equals 1, and it would also have a horizontal asymptote at y equals 0. But in addition to that, the graph of f of x would have a hole in it, and that hole would be located where x is negative 2. Okay, the graph of y equals 3 over x minus 1 doesn't have that hole. This graph by itself doesn't have that removable discontinuity in it. Right? But the graph of f of x would look like 3 over x minus 1, except when x is negative 2. Now, when x is negative 2, what would we get from this function? We would get negative 1. Okay? So the hole on the graph of this function here would be at the location where x is negative 2 and y is negative 1. That location would have a hole. Okay, that's the removable discontinuity for f of x. So again, so that graph of f of x and the graph of 3 over x minus 1, which we can call g of x, okay, they are the same each other except where x is equal to negative 2. Right? They are the same as each other except where x is equal to negative 2. Okay? And if that's the case, then if we take the limit as x approaches negative 2 of f of x, of this, it's going to be the same as the limit of this as x goes to negative 2. And that's the technique that we've used previously, okay, with removable discontinuities. And the last thing we'll take a look at here in this section from these notes will be the squeeze theorem, okay, outlined here. If the function we're interested in, f of x, if that's the function that we want the limit of, okay, if we're having difficulty establishing that limit, but if it turns out we can find a function that is below f of x and above f of x, so like a floor and a ceiling, let's say, that are either below or at or equal to f of x, okay? And if it turns out that the g of x, the floor function, so to speak, if that approaches some value as x goes to a, and if the ceiling approaches the same value as g of x did as x approaches a, okay, that is, they would close in and squeeze around f of x, forcing the limit of f of x to approach the same value as well. Okay. We'll investigate that a bit more later. Okay, so let's take a look at several of these laws together here. Let's take a look at we have the sum law. When you take the limit of a sum, it's equal to the sum of the limits. I remember that's if each of the individual limits exist on their own. The difference, similar. It's like saying we can distribute the limit. Okay. The limit as x goes to a is an operator. Okay. It operates on functions. It can't stand alone. So if I just write limit as x goes to 2, that doesn't mean anything by itself. It's like writing a square root symbol with nothing in it. All right, so the operator can't stand on its own, but when you apply the operator, the limit operator, to a function, right, then you can get an output from that. Okay, the limit operator, okay, has linear properties to it. One of a linear property is for instance, distribution. We can distribute the limit. So if we take the limit of a product of a constant c and a variable function f of x, okay, we can move the constant to the front. Okay. We can demonstrate that these laws are true all by doing graphical representations of particular examples, but we can also prove them more rigorously for generalized functions. That's something you might that you would probably see in an advanced calculus course or real analysis. Something that would happen after you're done with a few semesters of calculus and possibly heading towards graduate school. We can actually prove these for functions in general. The product law is essentially an extension of the constant multiple law. It's okay if f of x and g of x are both variable functions. I've already discussed that. Well, as long as each of the limits themselves would exist, okay, then we can write the product of the two. Talked about quotient law, very similar to product law. The power law, if you take the limit of a function to a power, let's say we want to take the limit as x goes to 1 of x squared. We could move the limit inside, and then so we can take the limit as x goes to 1 of x, and then the result of that can become squared. The limit of a constant as x goes to a, you just get the constant itself. That's easy to demonstrate by using the graph. 8, easy to demonstrate using the graph as well as the graph of y equals x. Okay. The limit as x goes to a of the nth root of x is equal to the nth root of a. This requires, though, that a has to be entirely within the domain of the function. That is, that you would have to be able to set up an open interval around a within the domain of the function. So, for example, okay, so it's going to be important that a is not at the end point of the domain. I'll show you a quick example why. Let's say we take the limit as x goes to 0 of the square root of x. Let's take a look at that example right now. Okay, the limit as x approaches 0 of the square root of x. Okay, so we have a function nth root of x where n, the index, is equal to 2. That's the square root function. Okay, the domain of this function is that x is an element of the interval from 0 to infinity. Well, notice that we're choosing a to equal 0 in this case. Okay, a is equal to 0. Okay, not a is greater than 0, like it says we need in the rule. Okay, so why does the rule not apply? That is, how come we can't just plug 0 into this? That's what the rule's trying to say. Can we just plug 0 into this and get our answer? Is this equal to 0? Okay, well, investigate the graph of this to determine why. Okay, take a look at the sketch of the graph y equals the square root of x. Okay, so that graph, it starts here, right, and opens upward, in this direction. Something like that, right? So here's y equals the square root of x. From our discussion already previously, the intuitive definition of the limit, why is it that the limit x goes to 0 of the square root of x, why is it that it does not exist? Take a look at the graph to see. So the reason why it does not exist is because we can't take the limit from the left. So require that what we need is we need to be able to evaluate the limit from the left, okay, and we need to be able to evaluate the limit from the right of a as well. Okay, if each of these exists, then if the left limit is equal to the right limit, okay, then it would be that the limit as x approaches a in general is also equal to that quantity, L or R. Okay, it's equal to both of those. Well, the limit from the left is the problem here, right? The limit as x goes to 0 from the left, okay, of the square root of x does not exist, okay, since the domain of this function is that x itself has to be greater than or equal to 0, right? There's no way to choose a value that is less than 0 to plug in. And that's the kind of limit we're looking at here. Okay? So this is to stress the point that if the function is not polynomial or rational, let me write that here, direct substitution property, when can we do a direct substitution? We require the function to be, right now, polynomial or rational. Okay, we can extend upon that later, but that in general there. Polynomial or rational. You have to be entirely within the domain of the function such that we can set up an open interval around the value a. Okay, this is a radical function, right? Square root. We have to be careful that we don't just plug the number in. If we did plug 0 in, we would get 0, but the limit is not 0 in this case. Now, if it was the limit as x goes to 1 of the square root of x, we can just plug in the 1 because the square root of 1 is 1, and we can see from the graph why that's true. If this is where x is equal to 1, we get y is equal to 1. Notice that for that case, we could approach from the left and approach from the right, and we would approach the same value. So if it was x going to 1, it would be perfectly fine to plug 1 in. Right? But because we are approaching 0, and 0 happens to be the end point for this domain, okay, then this does not exist. But if we wanted to evaluate the limit from the right, that is, if we were asked to find what is the limit as x approaches 0 from the right of the square root of x, here we are entirely within the domain, so we are only choosing values of x, okay, that are enclosed within the domain such that there would always be, for any value of x that we choose now, there would always be some value that we could squeeze between that and the endpoint 0, no matter how small a value we choose. Okay? And so this would equal 0. In other words, use the graph, limit from the right. Okay. Also, to continue to demonstrate this idea, what if we had the limit as, let's say x is approaching 3, okay, of the, let's do the fourth root here, okay, of 2x minus 6. Right? So something like that, okay? Well, the domain for this function is what? 2x minus 6 is greater or equal to 0. Okay. So that means that, 2x is greater or equal to 6, so x is greater than or equal to 3. In other words, we have the interval from 3 out to infinity. Well, we're taking the limit as x approaches 3, okay? But x is only greater than or equal to 3. That means we can't find the left-hand limit, right? That means the limit as x approaches 3 from the left, okay, of our fourth root of 2x minus 6, that does not exist. Okay? So since that does not exist, then the limit overall, as x approaches 3, of the fourth root of 2x minus 6, that does not exist as well. Okay? We can't take the limit from the left, because we're at the end point. So we have to watch out when we're dealing with functions such as these even roots. All right, the direct substitution property. Say it this way. If f of x is either polynomial or rational, remember that rational means a ratio of polynomials, and a is in the domain of f of x, then if we take the limit as x approaches a of that f of x, we can just substitute a into the function if it is polynomial or rational. So this is just equal to f of a. We'll extend upon this later. It turns out, in a couple of sections, we'll show that this in fact means, okay, this is the definition of continuity. Okay, this in fact means that f is continuous at a. In a couple sections we'll take a closer look at that. So really this is something we can apply to any continuous function. Okay, but for right now, just polynomial and rational. All right, so let's take an example. Let's do let's take the limit of a polynomial. I'll take the limit as x goes to 1 of 3x squared minus 6x plus 5. Real simply, by the direct substitution property, okay, we have f of x, which is a polynomial. Okay, so we can just substitute in. So 3 times 1 squared minus 6 times 1 plus 5 and evaluate. Right? So 3 minus 6 plus 5. 3 and 5 is 8. 8 minus 6 is 2. And we're done. Right? Really easy when it's a polynomial. Now, we could do the same thing with a rational. Let's say I was taking, how about the limit as, let's take the limit as x goes to 3, okay, of 2x plus 1 over 7x minus 2. All right? So 3 is within the domain of this function. All right, let's note that this function right here, the domain would be that x can be anything except for 2/7. Well, it's not 2/7, it's 3. So we can just use direct substitution and plug in the 3. 2 times 3 plus 1 over 7 times 3 minus 2. So that's 7 on top. 21 minus 2 is 19, so we're done. 7 over 19. Okay, relatively easy. Now, a little lengthier here, okay? Let's take a look at that first limit again, the limit with the polynomial in it, and see how all those laws, okay, several of those laws, limit laws, are actually showing up here when we try to evaluate this. Okay, first we have a difference and we have a sum. Okay, so using limit laws, Okay, first I can distribute the limit. We can write this as the limit as x goes to 1 of, let's see, 3x squared minus the limit as x goes to 1 of 6x plus the limit as x goes to 1 of 5. Oh, sorry, we're running out of room there. Okay. So we have a sum of limits. Okay, that's law 1. Law 1 is the one that says that if we have a sum and we're taking the limit of a sum, we can split it up. The limit of the first plus the limit of the second. And we have a difference here. That would be law 2 right there. Right? The difference law. We have a limit of a difference, then we can split up the difference. Both of these say that we can distribute the limit. Okay? We're also going to use the constant multiple law. We'll also be able to use this constant one. Okay? We'll be able to use 8 and 9. All of those together here. Okay? So the next thing we could say is, well, I have a constant here, 3. I can take the 3 out and multiply that times the limit as x goes to 1 of x squared. We could do that. Okay, so that's constant multiple law. Okay. That would be law 3, the constant multiple law. We use that again to take the 6 out. So 6 times the limit as x goes to 1 of x. Okay, law 3 again. And then at the end, well, here's what we're going to do here. The limit as x goes to 1 of 5, but 5 is a constant. The limit as x goes to a of a constant is always just equal to the constant itself. Okay, that's the constant limit law. That was law 7. Right, the limit as x goes to a of a constant is just equal to the constant. We have x going to 1 of 5, and that just equals 5. Okay. Now we can evaluate each of these limits. So we have here 3 times, and then this is going to be 1 squared. Okay, that was law 9. Minus 6 times, and this is just going to be 1. That was law 8. Okay, and then we still have the 5 right here. Okay. So that's law 9. Okay, that's law 8 right there. All right, and now at this point, we can just algebraically evaluate this. Right, follow the order of operations. So, right, so we have 3 minus 6 plus 5, and that equals 2. Okay, let's take a look at some more examples. How about combination? How about the limit as x goes to 4 of the square root of 3x squared plus 1 over x minus 1. This is a ratio, but it is not rational because the numerator is not polynomial. But this is built up out of a ratio of functions that we've already talked about. The denominator is polynomial, the numerator is a radical, right? A square root function. The domain for the numerator, by the way, 3x squared plus 1, notice that's always going to be positive. So the domain for the numerator, the domain for the square root of 3x squared plus 1, that's all real numbers. All right, because 3x squared plus 1 is not going to be negative. And 4 is certainly contained within that domain. So we can just plug the 4 in, right? We can do a substitution there. So let's try the quotient rule. The limit as x goes to 4 of the square root of 3x squared plus 1 over the limit as x goes to 4 of x minus 1. Okay, that's the quotient law. Sorry, I call it quotient rule. That's something else. This is the quotient law. Okay, that was law 5. Now we can run the limit on the top, and we would get, let's see, so we're going to get, right, 3 times 16 plus 1. And the denominator, we're going to get 4 minus 1. So we get 49 on top, square root of 49. The denominator is 3, so we get 7/3. So the limit is 7/3. Okay. Remember that if the denominator is equal to 0, then we have to be more careful, right? We have to, let's say we're running this limit as x goes to 1, where the denominator would then go to 0. If the numerator also goes to 0, then we should seek a way to remove the discontinuity. But if the denominator goes to 0 when the numerator does not go to 0, we should consider approaching the limiting value from the left and from the right, possibly using a graph, possibly numerically. And also a point on notation here. Okay, a point on notation. Very important here. I wrote limit in every step until I actually ran the limit, right? The first step where I didn't write limit was here. And that's because I had actually substituted the value into the expression because it was okay to do so. Okay. You must write the limit notation all the way up until the step where you actually run the limit. All right, so we're writing limit entirely in front of the expression until we actually put the until we actually run the limit. That's important in terms of the grammar of mathematics here, right? Remember, we're saying that when we're writing limit, we're actually thinking of and we're talking about choosing values that are not equal to 4. We're choosing values that are very close to 4. And under special circumstances, those two are the same thing. Choosing a number close to 4 is the same as choosing 4 under special circumstances only. And that's really where we have continuity, like with polynomials and rationals when we're within the domain. Okay, but we already saw that, like for instance with the square root function earlier, we have to be careful about plugging values in, okay, even if we are in the domain, because we were plugging in 0, which was in the domain, but it was on the end point of the domain, and that created a problem because of the type limit we were trying to run. Okay, so in general, it is not the same thing to write limit in front as it is to not write limit in front. Okay, so in general, writing something like limit as x goes to a of f of x is not necessarily the same as writing f of a. It requires that we know that the function is continuous. So if you just stop writing limit in front, okay, if you stop writing limit in front, it can create confusion for the reader. And your reader this semester will be me, and I'll be grading your work, right? So let's use proper notation. Okay, now what if we had taken x to 1, right? Let's say we had done limit as x goes to 1 as a reminder then, right? Because we did stuff like this before. 3x squared plus 1 over x minus 1. Now notice in this case that although the numerator is going to something finite, which in this case would be what? The square root of 4, which is equal to 2. Okay? But the denominator is going to 0, right? So we're getting 2 over 0. This is undefined. It is not indeterminate, right? It is undefined. And undefined, we have to answer the question, does that go to infinity? Does it go to negative infinity? Or is it that it does not exist? Which one of these conclusions do we reach here? We don't know yet because we haven't checked yet. Okay? We need to view the one-sided limits, okay, to know. Now in this case, what I could do is I could say I could note that the numerator, which is a square root function, has a range that is always greater than or equal to 0. So the square root of 3x squared plus 1, in fact, is always greater than or equal to 1, right, at its minimum, since x squared happens to always be positive, okay, or non-negative, that is, the smallest that x squared can be is 0, well then the smallest that 3x squared plus 1 could be is 1, and the square root of 1 is, well, 1. If you were to graph this, you would see that the graph of it only exists above or equal to 1. So that means that the numerator here, this 3x squared plus 1, okay, is guaranteed to always output a positive quantity, no matter what was happening with x anyway. In fact, we can see with that positive quantity, it's actually positive 2. Right? It's always going to be close to 2 when we run the limit there. So the actual sign of the ratio for this example is completely determined by what the denominator happens to be doing. That is, if the denominator, right, if the denominator is going to be always positive when we run this limit, then we'll have a positive over positive. And it's like if we divide a positive 2 by a really small positive number, we would get a really large positive number and the limit would be infinity. But if the denominator is always going to be negative, well, then we would have a positive number on top divided by a really small but negative number on the bottom. And then the ratio would go to negative infinity. But if the denominator flip-flops, if it's depending on the direction we approach 1, if the denominator is sometimes positive but sometimes negative, then the ratio is bouncing between positive infinity and negative infinity. And in that case, since the two limits don't agree, we would have does not exist. In any case, we'll have to take a look at the one-sided limits. Okay? So, let's take a look at the one-sided limits for the denominator. The limit as x goes to 1 from the left of x minus 1. Okay? This is saying that we are choosing values that are a little bit less than 1 for x. And then if we subtract 1 from that, okay, we would get a value that is a little bit less than 0. Okay? So I'll write it like that. So this is going to 0, but it's going to 0 from below. But the limit as x approaches 1 from the right of x minus 1, that is also going to go to 0. But notice we're choosing values of x that are a little bit more than 1. So this difference is going to be a little bit more than 0. And that makes all the difference in the world. So because of that, since x minus 1 in the denominator, okay, from one side goes to a positive small number, and then the other side goes to a negative small number, okay, then that means that the limit, let's see, the limit from the left of our square root of 3x squared plus 1 over x minus 1, right? Now this is going to be 2 on top, but the denominator is going to be a really small negative number. That means this is going to negative infinity. But the limit from the right, right, we get 2 over a really small positive number, so this goes to positive infinity. And since those two don't agree, okay, then this limit here does not exist. Okay. Now, by only varying this expression just a little bit, this can change from not existing to being either infinity or negative infinity. So suppose I went in and squared this denominator like that. And suppose that this was the limit you were asked to evaluate. Okay, showing all your work, proper notation, okay, so you can show me how you know the limit is what you say it is. Well, if we start by running the limit in the numerator and denominator, writing down here the little ratio of the results there, we still get 2 over 0. Right? We're still going to get 2 over 0, which is undefined by plugging in. So we still have to answer this question, which one of these is it going to? Okay. But now, because we're squaring x minus 1, then that means we would have the square of this, we would have the square of this, and notice that when you square this quantity now, you're going to be squaring a negative. Well, that means you're going to end up with a positive. Now you're going to end up with positive from either direction. And if that's the case, you end up with positive from either direction. The fact that we squared this changes the answer to infinity then. All of a sudden, the limit would go to infinity. What about if I were to put a square right here? X squared minus 1 like that. We're still going to get 2 in the numerator when we run it through, and we're still going to get a 0 in the denominator. So it is undefined. So evaluate this limit right now. Look at it from the left and the right. Okay? From the left and the right to indicate which answer are we going to get now. Is it infinity? Is it negative infinity? Or does it not exist? So you found that the limit as x goes to 1 from the left. So if you're choosing values of x that are a little bit less than 1, note that choosing something that's a little bit less than 1 and then squaring it, you're also going to get a result that's a little bit less than 1. So from the left, you would get a negative number. And from the right, you're choosing a value of x that's greater than 1. But you square a number that's greater than 1, you're going to get a number that's greater than 1. And then when you subtract 1 from that, you're going to have a positive result. So we're going to be, so limit from the left would output negative infinity of the ratio, and the limit from the right would output positive infinity for the ratio. So this limit with the square on the x, that limit would not exist. All right, let's try another example. The limit as t approaches 0 of t to the negative 1 minus t to the negative 2. Little negative exponents in there. In other words, rewriting this, limit as t goes to 0 of 1 over t minus 1 over t squared. Now note, if we take a look at each of these limits independently, what happens? The limit as t goes to 0 of 1 over t. Right? Graph of y equals 1 over x, or 1 over t. It looks like this, right? Vertical asymptote right here at t is equal to 0. Okay, but this limit then, we can see graphically, does not exist by itself. But the limit as t goes to 0 of 1 over t squared, okay, now the graph of y equals 1 over t squared, okay, also has a vertical asymptote at t equals 0, but it looks like this. Okay. And in this case, this equals infinity. Okay, but we can't take something that doesn't exist and then subtract infinity from it. That would suggest that the whole thing doesn't exist. Okay? Well, here's the thing then. We can't do this. We can't split it up. And we can't use the law as stated here, this difference law. We can't split this up into separate limits and then evaluate the results because one of those two limits does not exist. Does that mean that the result does not exist, though? Not necessarily. It means that we can't use the law that's stated here because one of the two independently didn't exist. Okay? It doesn't mean we can't evaluate it, though. So let's try to find another way. Like we did with difference quotient before. Maybe we can simplify before we run the limit. Okay? So limit as t goes to 0. Let's combine these with a common denominator, which would be t squared. So that would be t over t squared minus 1 over t squared. In other words, t minus 1 over t squared. Okay. All right, so now we have this ratio, okay, or this quotient now, okay? So let's try to run the limit on this quotient. Okay, the numerator, all right, I like to write this below the equal sign when I'm just testing it out here. As t goes to 0, the numerator is getting really, really close to negative 1. But the denominator is getting really close to 0. How is the denominator getting close to 0? Well, notice that regardless of whether t is positive or negative, the squaring of t is always going to result in a positive quantity. So the denominator is strictly positive. So we have a negative finite number on top, but then we're dividing by a really small positive number. So the ratio will be really large, but negative. And so this limit is negative infinity. Okay. So we couldn't break it apart into individual ones. For this particular example, we were able to combine these rational expressions. We were able to combine them into a single quotient, okay, and then it was able to run that limit on that quotient. All right, let's take a look at another type of example, piecewise. Okay, or let's do an indeterminate form. Okay. So we have several indeterminate forms. The limit as x goes to 2 of 2x squared minus 5x plus 2 over x squared minus x minus 2 is an example. Okay. We don't know it's indeterminate until we try to run the limit. Now, plug it into the numerator, we get 2 times 4, which is 8, and then minus 5 times 2 is 10, and then plus 2. In the denominator, we have 4 minus 2 minus 2. Notice this is going to give us 0 over 0. That is our indeterminate form. And when we get the indeterminate form, means we could expect a removable discontinuity here. We have to find a way to remove it. So recall the factor theorem for polynomials. Okay? If a polynomial were to equal 0 for some input, in this case the input is 2, then that polynomial must have a factor x minus c, where c is the 0. Okay? So use the factor theorem. Right? If p of c equals 0, where p of x is a polynomial, then x minus c must be a factor of p of x. So we have the limit as x goes to 2 of, the numerator would have an x minus 2, okay? Because we know plugging 2 in would give us a 0. And the denominator also has to have a factor of x minus 2 because the denominator is polynomial and it goes to 0. What are the remaining factors? Well, then up top we would have to have a 2x, okay, and then minus 1. Okay, we can just check that by foiling 2x squared, and we get a minus x minus 4x combined to a minus 5x, and then these multiply to a positive 2. The denominator, take out x minus 2, we would be left with an x plus 1. Now we can remove the discontinuity and rerun the limit. Limit as x goes to 2 of 2x minus 1 over x plus 1. Okay, now we are within the domain of this rational function. Okay, so we can just plug this in. So you get 2 times 2 minus 1 over 2 plus 1. Right, what does that give us then? Okay, so we get 4 minus 1 is 3, 2 plus 1 is 3, 3 divided by 3 is equal to 1. Okay, so this limit's equal to 1. Alright, so let's get away from polynomials here. Let's try another type of an example. The limit as x approaches 5, square root of x minus the square root of 5 over x minus 5. So first I'll check to see what's going to happen if we just plug this in, noting that we're plugging into a square root function here. And the domain of that square root function, square root of x is greater or equal to 0, which contains 5 entirely within its domain. Okay, so it's okay to plug 5 into the square root function. It wouldn't be okay to plug in 0 because that would be the endpoint of the domain of the square root function, as we talked about earlier. But I'm going to plug in the 5 and see what happens. We get root 5 minus root 5, but that equals 0, and the denominator is 5 minus 5, and that's also 0. So it is indeterminate. Okay? Indeterminate. But not polynomial in the numerator. Right? So factor theorem doesn't apply unless we can transform this into an equivalent ratio where the numerator is polynomial. And we can do that here. We can rationalize the numerator. Rationalize the numerator. That is, transform the numerator, okay, into a rational expression. Okay? And that can be done by multiplying by the conjugate. Okay? So multiply by the conjugate of the numerator. Okay, so the conjugate of the square root of x minus 5, minus the square root of x minus the square root of 5, the conjugate of that would be the square root of x plus the square root of 5. So the limit as x goes to 5 of the square root of x minus the square root of 5 times the square root of x plus the square root of 5. And then we'd have to multiply the denominator by the same quantity. Right? So if we have an a minus b situation, we multiply by a plus b, because when we multiply those out, we get a squared minus b squared. All right? The difference of two squares. So we'll do that right now. We'll multiply the numerator, foil it out. We get x minus 5 then for the numerator. And the denominator, notice we already have an x minus 5 down there. I do not want to distribute that. I want to cancel it. So we have an x minus 5 on top, but we already have an x minus 5 on the bottom. And now we get to remove the discontinuity. And then we can rerun the limit. x approaches 5. I'm writing limit in every step, right? Every step I'm using this limit notation before, okay, up until the point where I actually run the limit. And that's what's going to happen right now. Now I'm going to plug 5 into here. Again, it's within the domain of the square root function entirely, not on the endpoint. And we get 1 over root 5 plus root 5. In other words, 1 over 2 root 5. All right, let's do another rationalizing. Let's now rationalize the denominator of this result. Clean up this answer. So we can rationalize the denominator here by multiplying top and bottom by square root of 5. That would give us root 5 on top, and it would give us 2 times 5 for the denominator, so we would have the square root of 5 over 10. Where now the denominator is a rational number. Okay. So if you're checking your answers in the textbook, or if you're given instructions where the denominator needs to be rationalized as a simplification process, then this is something you would need to do. If the instructions that I give you, if I don't give you in the instructions that you have to rationalize the denominator, then I'm not looking for you to necessarily do it. But it certainly could be the case that if you solved a problem like this and you got an answer like this, if you look up the answer in a textbook or on a resource, you might not see that answer. You might see this one. And it's helpful to know how to transform it. All right, this is a common simplification to rationalize a denominator. However, the process of rationalizing was important here. We rationalized the numerator here because, first, we noticed we had an indeterminate form, 0 over 0, which suggests that we have a removable discontinuity. So we needed to find a way to remove it. But the numerator was a radical, or a combination of radicals here, a two terms that were square roots, not polynomial. And rationalizing, that's multiplying both the top and the bottom by the conjugate of the numerator here, that gave us a polynomial, right? Without changing the value of the fraction. We multiply the top and the bottom of the fraction by the same quantity, then the fraction itself is still the same. It's the same quotient. But we've transformed it so the numerator is now polynomial. All right, and notice that that then allowed us to be able to cancel a factor at that point. All right, let's try an absolute value example now. Okay, let's take the limit as x goes to 0 of the absolute value of x over x. And so how do we do this limit? Consider that the absolute value of x is piecewise. It is written as x if x is greater or equal to 0, but it is negative x if x is less than 0. That is, we're going to switch the sign if x was negative already. Okay, how does that apply to this? Well, that means that the absolute value of x over x can be written as, if x is greater or equal to 0, this is equal to x over x, right? This is equal to x over x, which is just 1. But if x is less than 0, then this is the numerator would be negative x, right? So we would have negative x over x, but that is always equal to negative 1. Okay? So this tells us what this function is going to look like graphically. Okay? The absolute value of x over x, if we graph that, the absolute value of x over x, it looks like this. It looks like the constant function y equals 1 if x is greater or equal to 0. So from 1, we fill in solid point, and this extends outward to the right. It goes like that. And if x is less than 0, then this is always going to output the constant negative 1. So let's go down to negative 1. This doesn't happen when x is equal to 0 now. Okay, so this is open. And then this extends outward in this direction like this. There's our graph. For this function, that's the graph. So what's the limit? Well, we have the limit as x approaches 0 from the left of absolute value of x over x. That's as we are moving along the graph like this. What y value are we approaching if we're approaching from the left? Okay, we're approaching the y value of negative 1. Okay. But the limit as x goes to 0 from the right on the same graph, and we are approaching this way, we would be approaching the y value of 1. And these do not equal each other. Therefore, this limit in general for x approaching 0, that limit does not exist. We'll take a look at one of the exercises from the worksheet with the absolute value in it. We'll take a look at this one right here. Limit as x approaches negative 2 of 2 minus the absolute value of x over 2 plus x. Now, so this one's a little bit different than the previous one. First, we're not allowing x to approach 0. Notice that when we have x approaching 0 in the absolute value of function, 0 is exactly where the behavior of the absolute value changes. It switches. But if we plug in a number like negative 2, we would be entirely on one of these branches. Right, if we take a look at y equals the absolute value of x, for instance, all by itself as a graph, right, it looks like, V-shaped graph, right, y equals negative x, y equals positive x. And if we go to where we're at negative 2, there's no funny business going on there, right? From the left or from the right, it's the same thing. It goes to negative 2. Okay, and there's no change in behavior like there is at 0. At 0, the issue is that the behavior of the function is changing instantaneously. Right? It's not a smooth curve. It's just an immediate change. It's a corner. Okay, so that's not an issue. So we can just plug in negative 2, and maybe that'll work. Well, what happens when we plug in negative 2? The numerator would become 2 minus the absolute value of negative 2, but that's 2 minus 2, and that equals 0. And the denominator, 2 plus negative 2, that equals 0 as well, and that's indeterminate. Okay. So how do we deal with this indeterminate form here? Well, we can deal with the absolute value in a piecewise sense. Again, the absolute value of x is x when x is greater than or equal to 0, but an opposite of x if x is less than 0. So, what does that mean about the function 2 minus the absolute value of x over 2 plus x, okay, in a piecewise sense? Okay, the difference is going to be, for absolute value of x, the difference would be if x is greater than 0 or less than 0. That's where the difference happens, okay? If x is greater than 0, right, if x is greater or equal to 0, then the absolute value of x is just x, right? The absolute value of x would just be x. So then we would get 2 minus x over 2 plus x, if x were greater or equal to 0, right? And what about if x is less than 0? If x is less than 0, then the absolute value of x, all right, then the absolute value of x itself would output negative x, or the opposite of x. That is, we would have 2 minus negative x over 2 plus x, if x is less than 0. Well, how does that simplify? 2 minus negative x is the same as 2 plus x. And 2 plus x over 2 plus x, okay, is just equal to 1. All right? So, since x is approaching negative 2, and we're saying that, therefore, not that x is equal to negative 2, remember, but x is very close to negative 2. Regardless of whether we're approaching from the left or the right, notice that that means, for this case, x will be less than 0. Okay? X is nowhere near 0. Okay? In terms of closeness, it's not near 0 at all. It's close to negative 2, so it's guaranteed negative. And if x is negative, then the output of this quotient is just 1. So the limit, well, I can just write it up here at the top. Right, so this limit is, of course, because x is negative here, we're going to end up with the limit as x goes to negative 2 of 2 plus x over 2 plus x. Polynomial over polynomial, 0 over 0, we get to cancel the discontinuity, All right, so this is the same as the limit as x approaches negative 2 of 1, and the limit of a constant is just equal to the constant itself. So this limit is just equal to 1. And so that's one way we can deal with an absolute value. Deal with the absolute value by rewriting it piecewise. Okay, the changeover is not always going to happen at 0. What if we had the limit as x goes to 6 of x minus 6? Something like that. Right? Well, absolute value of x minus 6 is equal to just x minus 6 as long as x minus 6 is greater or equal to 0. In other words, if x is greater or equal to 6. All right? If x is a number like 7, then you don't need the absolute value anymore because 7 minus 6 is positive, and you don't need the absolute value of that. But if x is less than 6, right? If x is less than 6, like a number like 5, well then 5 minus 6 is negative 1, and a negative, the absolute value is going to flip its sign. So this would output, we could write this as 6 minus x. Or we could write this as negative x minus 6 is another way we could write that. So we're saying whatever the output would have been, up here, we're taking exactly the opposite of that under the condition, right? Under the condition that the expression on the interior would be negative. Right. The graph of this absolute value of x minus 6, okay, is going to look like the absolute value function, except it's shifted 6 units to the right. So it is a V-shaped curve, okay, like that. Okay, and it's also, by the way, what happens when x is equal to 0, you're going to get y is equal to 6 as well, right? Because the absolute value of negative 6 would be positive 6. Okay, so what's this limit right here as x approaches 6? We can use the graph and find out. From the left, we're approaching what y value. From the right, we're approaching what y value. That y value is 0. All right, so that's good with absolute value. So in general, if you're doing a piecewise, the limit of a piecewise function, sketch the curve is a helpful approach to take. That's if you're looking at the limit where you might be crossing over from one piece to another piece. Let's say we take the limit as x goes to 2 of f of x if f of x is equal to 3x plus 1, okay, if x is less than 2, but how about 2x times x minus 1 if x is greater or equal to 2? Okay, so we're taking the limit as x approaches 2 of this function. So we need to consider left and right-hand limits, right? Look at the one-sided limits. Okay, we need to examine those. What is the limit as x approaches 2 from the left of f of x versus the limit as x approaches 2 from the right of f of x? Given that 2 is where we switch from one to the other. Now, we could do a sketch of this. Okay, you could graph it. I'm also going to look at this just straight up algebraically here. Okay, if x is less than 2, that's if we are on this, okay, if we are looking at the limit from the left, okay, so x is less than 2, right? Because we're to the left of 2. That means f of x looks exactly like this piece, 3x plus 1. So as x approaches 2 from the left of f of x, it's x approaching 2 from the left of 3x plus 1. This is polynomial, so the direct substitution property applies. We can just plug the 2 in, and we get 3 times 2 plus 1, and that equals 7. Okay, so this limit from the left is 7. The limit as x approaches 2 from the right of f of x, that means that x is now greater than 2, not equal to 2, right? We're in a limit. If x is greater than 2, then we must be on this piece, 2x times x minus 1. So when we run that limit as x goes to 2 from the right of f of x, it's the same as the limit as x goes to 2 from the right of 2x times x minus 1. Now we have a product. Okay, we can either distribute this and then we have a polynomial, or we can take the limit of each element within the product by limit laws, because each of those limits is going to exist either way. So like the limit as x goes to 2 of 2x times the limit as x goes to 2 from the right, in both cases, of x minus 1, for instance. Okay, so we get 2 times 2, so this is one that's 4, it's a direct substitution. And this one is 2 minus 1, which is 1. All right, direct substitution there as well. So this equals 4. So the limit from the right is equal to 4. But the limit from the left is not equal to the limit from the right. In other words, 7 does not equal to 4. Okay? So the limit in general as x approaches 2 of f of x for this piecewise example, this limit does not exist since the left and right limits are not equal to each other. Okay, so please pay careful attention to the notation when you're using a one-sided versus a two-sided limit, that you're writing limit all the way through until you actually do the evaluation of the limit. Notice where I stop writing limit. So there's one more thing to look at in this section, and that is the squeeze theorem. Take a look at that in the textbook. We'll try an example. So we're primarily interested in taking the limit of the middle function here, which they're calling g of x. So they're saying that if g of x is already bounded between f of x and h of x, where f of x is no more than g of x, so less than or equal to g of x, and h of x is no less than g of x, so h of x, you can think of f of x as a floor function and h of x as a ceiling function. They could be equal to g of x at certain values, okay, but they are bounds, a lower bound and an upper bound. We can visualize this, okay, as so there is an upper function and a lower function, and then there is our function contained between them, okay, within some interval around the limiting value a, okay, so that it's relevant to the squeeze theorem. So this doesn't have to be true necessarily outside when we're far away from a, but when we are near a, this would need to be true to use this theorem. That the function we're interested in this case, g is the function that we're interested in for their example, there is a function that is below the floor, which is f, and above the ceiling, which is h, but there can also be points where they are all equal to each other. And in fact, it's going to be important that they do merge specifically at a in order for the squeeze theorem to apply. All right, so here we go. So if f of x, as x approaches a, if f of x is going to some value, they're saying it's L, and if h of x is also going to that same value L, okay, but g of x, if that's always stuck between those two, then g of x has to be squeezed to that value as well. Here's the first animation demonstrating squeeze theorem here in the book. Okay. So x is approaching a from both the left and the right. All right, so we have moving points on h of x and on f of x, right? And they merge. Okay, and so what is happening therefore with g of x? No matter what g of x is doing, otherwise, because it's always stuck, squeezed between those two functions, as it approaches a, it's going to be forced to the same limiting value L as the lower bound and the upper bound. So here's an example. X goes to 0 of x squared times the sine of 1 over x equals 0. Okay. In order to use the squeeze theorem here, okay, we'll go back to this note in a moment why we cannot write this as a product. To use the squeeze theorem, take note, the sine of anything, first off, 1 over x, right? 1 over x by itself as x goes to 0, that, recall, does not exist, because if x is positive, then this is going to positive infinity, 1 over x is. But if x is negative, then 1 over x is going to negative infinity, right? So 1 over x doesn't exist by itself. The sine of 1 over x is another issue. We'll take a look at that in a moment. Okay, But something we do know about the sine function itself, the sine function is bounded. The sine function is a function that has a lower bound and an upper bound. What is the lower bound of the sine function, and what is the upper bound of the sine function, no matter what value we plug in? The sine function, the sine of anything, is always going to be greater or equal to -1 and less than or equal to +1. So the sine of 1 over x, no matter what x we choose, is for sure always going to be between -1 and 1, as long as the sine of 1 over x exists. And the sine of 1 over x will exist, as long as x is not 0. Is x 0? No. X is getting close to 0, but it never actually gets to 0. So regardless of whether x is positive or negative, the fact still remains. The sine of 1 over x will always be bounded between -1 and 1. Now, our expression we're trying to take the limit of wasn't this one. We were trying to take the limit of x squared times the sine of 1 over x. Now, if the sine of 1 over x by itself, right, is bounded between -1 and +1, then the product of x squared and sine of 1 over x is bounded between -1 times x squared and +1 times x squared, right? Because the sine of 1 over x is between -1 and +1. And so, right, just multiply x squared times this, and times this, and we get this result. Now we have the function we're interested in taking the limit of here in the middle, squeezed between these two. And the value we're trying to take the value in which we're trying to get x to approach is 0. What happens? This is important that we can only apply a squeeze theorem if both the lower bound and upper bound approach the same value as we run the limit. That's the only way it gets squeezed. And in this case, that happens to be what happens. The limit as x goes to 0 of x squared is 0, of course. So this, the lower limit here, the floor function, that approaches 0 as x goes to 0. And the ceiling also approaches 0. And since this is going to 0 and this is going to 0, then that means the middle function here is bounded between 0 and 0, which forces this function to be squeezed to 0. And here's what it would look like graphically. This is the graph of x squared times the sine of 1 over x. So we have the lower bound, the floor function, was y equals -x squared. Right? The negative came from the lower bound of the sine function. And the ceiling function is y equals x squared. So we can draw those two parabolas and then plot the sine curve as it is getting squeezed in between those. And this is a cool little animation here that they did to show sketching floor and ceiling, and then show how we can sketch the function and we can in fact run the limit now from the left and the right, okay, to see geometrically, right, how this limit is being evaluated. Sorry about that. Flipping around here. Come on, run the animation. Right, so there we go. Pretty cool. So our function we're interested in is the red one. That's x squared times the sine of 1 over x. We have a ceiling function and a floor function, and the squeeze theorem applies here because the ceiling and the floor both merge as we get close to that value a, which in this case is 0. So there's the squeeze theorem. Now, this is an interesting note here. I said first, let's note that even though it would look like this could give us 0 if we ran it this way, we actually can't do it this way. This is incorrect to write it this way, to take the limit of this and the limit of that. Because, that is, we cannot use the limit law for the product law. Because this limit here, as x goes to 0 of sine of 1 over x, okay, it turns out that that one does not exist. And it references that example, another page in the book. So I opened that one over here so we can take a look at this is a similar example, okay? So this one has pi over x in it, right? So it's just modulated by a constant there. This is 1 over x, okay? So sine of 1 over x, this is the sine of pi over x. And the limit is going to be the same, overall the same result in the end, okay? It's a little easier to look at it, at this result when we use pi though, okay? So it says, just evaluate this limit. And so this is just back in section 2.2 where we're dealing with using graphs of functions. Notice it's undefined at 0. But of course we can choose values that are very close to 0, both from the left and from the right, and plug them in. And so it does that. It says, well, let's choose a bunch of numbers to plug in. Let's plug in 1, 1/3, 0.1, right? 1/2, 1/2, 0.01. And they should do the same with negative quantities as well, right? So they got positive quantities getting closer to 0, and then you can do the same with negative quantities getting closer to 0. But by choosing all these values that they happen to have selected here, they keep getting 0 as the output of this function, as you can see here, which seems to indicate that this function is going to 0 because we're choosing values that are getting closer to 0 to plug in, and the output keeps being 0. So it looks like the output's going to be 0. But it actually, there's a flaw here in that it just turns out that the numbers they were plugging in happened to be outputting 0 every time. And if they happened to choose a number that was not in this list, if they chose a different number, it could have demonstrated that no, this wasn't really going to 0. We can better see that that's the case by looking at the graph. We're saying, no, our guess is wrong. Although f of 1 over n is always equal to sine of n pi, right? So the sine of pi over x, if x is 1 over n, where n is an integer, okay, then you're always going to get that integer times pi, and the sine of an integer times pi is always equal to 0. But what if they had chosen something like 2/3 to plug in, right? If they had chosen 2/3 to plug in, they would not have received 0 as the output. So we have to be careful. But they say, well, let's take a look at the graph. Here's the graph of the sine of pi over x. And what's happening as x is approaching 0? Right? This thing is oscillating very, very fast, and it's getting more and more close together, right? Very dense right there. Okay. And is it approaching 0? And the answer is no, it's oscillating, right? It's oscillating very, very rapidly as it gets close to 0, and in fact, it keeps moving. It's not settling down to 0, and this is a requirement for limits. It has to be getting closer and closer to the limit value if the limit exists. But this is not getting closer to a value. Every time we look at it, an instant later, it's somewhere else. It's bouncing between 1 and -1, and it's hitting all the values in between. And that just keeps happening. So if it's going to more than one quantity, as we try to approach 0, it just keeps going to more than one quantity, and it doesn't settle down, then actually the limit does not exist. That's a complicated one there. Okay, but it is one that demonstrates, okay, when we cannot use the product law is what's important here. This limit by itself, the point is this limit does not exist. And because this limit does not exist, we can't write the limit of this product as the product of the limits. We can't do that. So squeeze theorem shows up every so often. You don't know necessarily when it's going to show up. It's just, techniques sort of fall apart sometimes, and you need something else. So you try something and see if it works, and if it doesn't work, it doesn't work. Okay, but here's a couple of examples here where you could use the squeeze theorem, and I'm going to do this one right here to demonstrate how to use the squeeze theorem appropriately then. Okay, the limit as x goes to 0, but it's remaining positive. Notice the reason I put that in there is because, well, we have the square root of x. Right, and of course this, that would be a problem. We can't plug in numbers into this. We cannot plug in numbers that are less than 0 because we have a square root here. And then e to the power of the sine of pi over x. There's that sine of pi over x thing again. Okay, but we're going to use the squeeze theorem the same as they used the squeeze theorem in that other example. So let's try this one right now. Okay, so we have the limit as x approaches 0 from above, square root of x, e to the power of the sine of pi over x. Right? Now, the sine of pi over x is bounded between -1 and +1 for all values of x other than 0, right? But x is not 0. Okay, so this is true, right, for all x not equal to 0. Okay, so that means then that e to the sine of pi over x, okay, since y equals e to the x is an increasing function, then e to the sine of pi over x is also bounded, and it's bounded between e to the -1 and e to the +1. Okay. So that's true because this exponential is a growth function. Now, if we can multiply now everything by the square root of x. Okay, so we get square root of x times e to the negative 1 is less than or equal to the square root of x times e to the sine of pi over x, which is less than or equal to square root of x times e. Okay, and now we can take the limit of the floor and the ceiling functions as x approaches 0 from above. Right? So we have the limit as x approaches 0 from above of the square root of x e to the negative 1. I can also write that as the square root of x over e, right, where e is constant. Okay. And that limit, well, we've got the numerator going to 0, but the denominator is e, and 0 divided by constant is just 0. So this, right, is going to 0. And on the right here, the ceiling, we have the limit as x approaches 0 from above of the square root of x times e, okay? And that is going to 0 times e. E is just a constant, right? So we can factor out the constant limit as x approaches 0 from above the square root of x. So this is e times 0, which is equal to 0. So this is going to 0. Okay. So this approaches 0 as x approaches 0 from above, and this approaches 0 as x approaches 0 from above. Okay. So therefore, I'm going to use 3 dots here. So that's therefore the limit x approaches 0 from above of the square root of x e to the sine of pi over x. Therefore, that equals 0 by the squeeze theorem. Okay. All right, and that's it. So we're saying that the limit as x goes to 0 of root x over e is less than or equal to the limit as x goes to 0 of the square root of x e to the sine of pi over x is less than or equal to the limit as x goes to 0 from above of the square root of x times e, right? So this limit is 0, this limit is 0, and therefore, by the squeeze theorem, this limit is going to be 0 as well. All right. So a lot of techniques, laws, okay, properties. Okay. There are too many of these types of examples to go over, so just give you some representative examples and how we might approach some of these, and then sort of, cut you loose and let you try out some on your own and see what you can figure out. Please make sure you're using proper notation, writing the limit when the limit needs to be written. Okay. And remember that you, in some cases, you have to check the one-sided limits. You have to look at the limit from the left and the limit from the right. And it's important that if that's what you're doing, that you're showing your work in a way where the reader can understand what it is that you're actually attempting. If you have any questions, you can let me know. Okay, take care.